I don't know most of you on this thread, though I feel like I know Bob because he reviewed one of our papers last year, and also I read The Sky is Your Laboratory last summer. But I wanted to show you how Desmos works. This is the main desmos.com website, and you click Start Graphing, and it'll give you a blank graph. So I'm going to enter A equals 4, and B equals 9. Notice it automatically added some sliders for those. And then I'll do R squared equals X over A squared. Let's see, how do I get out of that? Plus Y over B, and square that. And it gives you an ellipse, and I can use the R slider to make it bigger or smaller. I can change A or B using these sliders, and that's what Desmos does, is it graphs functions in this way using parameters. So Hagen's tool graphs a more complicated ellipse using more parameters than A and B, but it does the same sort of thing as is shown here, and you can play with that. Now, when I click this little share graph button, it will give me a URL, which is always going to look like this when you go to it. So it's going to be live always. No matter what I do to the graph that you arrive at when you click this link that it gives you from Share Graph is going to be the same as what it looks like now. So one of the amazing things also about this tool is what it makes possible with analyzing individual data points from the Washington Double Star Catalog. This orbit, let's see if I can find a picture of it actually. This is what it looks like when you request the data from the Washington Double Star Catalog, and you can look at its published orbital parameters, and this is the published fit to the data. But if you take the raw data that will be returned from a WDS data request and plot it, it doesn't look like that. It looks like a cloud of data points. Some of them were rotated incorrectly, and Desmos can help you figure out which ones. So in this spreadsheet that I forwarded to you, this is the rightmost tab. It says 14.0, and then the 03337 plus 5752 is the Washington Double Star Catalog ID. And all of the Desmos plots are links. So if you click on, for example, this Desmos plot with the enormous residuals, it'll take you, it'll open up your browser and take you to a plot in Desmos. And it will always be live because, again, this share graph thing preserves the information that was at that URL before. And you can pick out the points that were incorrectly rotated. So watch this, for example, this one I think was, and if I remove these negative signs, you're gonna see the residual disappear as the point snaps into its rightful place on the ellipse. So watch this. Taking out that one and taking out that one. And it's beautiful. It snaps right to where it belongs. If I put it back, watch, I'm gonna put it back. Goes there and over there. That was entered into the data set incorrectly rotated. So when they fit it, they must have used the correct rotation, but somehow in the data, it's now incorrect. And same with several of these other ones. And you can watch them one by one. I'm just going to do it again because I think it's so cool. See, getting rid of that negative sign. Getting rid of that negative sign. So then you can pick out which data points have these problems. I think that's one of the most useful things about Hagen's tool. One of the many. There are other useful things too, obviously. But here's one other point to make about that. So here is Hagen's blind test that Richard Harshaw sent to him to fit. And Hagen's fit is in green, Dr. Hartkopf's is in purple, and the difference is pretty clearly the weightings, because the purple one seems more constrained to hit these bottom right points, which were presumably taken later with more exact techniques, and the green is a more general fit to the entire data set. So Desmos got a fit that was within a few percent of the orbital parameters that Dr. Hartkopf got. But I don't think it would be useful to include weightings in Desmos, because Desmos's power is to let you see things graphically, and weightings aren't something that you see graphically as well when you're fitting it anyway. And the way to fit this is to use more than 50 points. I think this one had like 100 and some, and Desmos only takes 50 at a time by copy paste, otherwise it runs more slowly. But then once you have the green, the idea is that you can get to the purple by putting those initial values into a gradient descent algorithm, or Hagen now uses differential correction and is actually working on yet another technique for getting to an orbital solution from a good best guess. And I think Desmos's purpose is to get you to a best guess, and it does that really well. It gets really close. And then the more mathematical technique, which would use all the data points and incorporate the weightings, would be the right thing to do to get to the full orbital solution. The cool thing is that my students can get to the best guess, right? The initial value problem is the title of the paper, and the initial values are really good. And even not only my students, my 11-year-old can get to a best guess just visually by playing around with the parameters on their sliders, which Desmos provides, and looking at the R-squared calculation and getting that closer and closer to 1. So that's amazing. That's super cool. And I think that the tool has incredible pedagogical value for that reason. And I wonder how useful it would be to try to make Desmos do weightings too. I think that that's the wrong tool for that job, even though it's an amazing tool for this job. So anyway, I hope that gives you an impression of how Desmos works and how it's used for this tool, but it's pretty awesome. Thanks. Bye.